Welcome to vapor pressure and changes of state, or phase changes. So, we know that we have three main types of phases. We have solids, liquids, and gases, and we also have plasmas. So, let's look at solids. Okay, so I'm going to put those down here. Solids. If we plot them on terms of enthalpy of the system, in order to get, remember, enthalpy is related to the heat. So as we change from, say, solids to liquids, in order to get from solid to liquid, we have to heat it up. So we're moving up on the enthalpy, right? We're putting in energy to change from solid to liquid phase, right? So as we move from here to there. Now, that process, the solid to liquid process, what do we call that? We call that melting. Now, in science, sometimes we call that fusion. Now, this is different than, say, nuclear fusion, which means coming together, right? You've got two nuclei, and you squeeze them together, and you end up with one nucleus. So, this is because it seems a little strange to be calling the solid to liquid process fusion. Most people would think that, it should be the liquid to solid process fusion because you're fusing a solid out, right? Well, this is because fusion is a Greek word, and that Greek word meant melting together. And so the nuclear fusion part takes the together part, you're creating one thing, but the solid to liquid, the melting, is the melting part of it. So you're melting your solid, right? So you're not melting it together, you're melting it apart. But that's why we call it fusion. So now we can do the opposite. We can go from a liquid back to a solid, and of course that's called freezing. Now we also have another phase up here, the gas phase, and the horizontal axis here is totally meaningless. I just wanted to be able to space out our transitions here. So we can transition from a liquid to a gas, and that's called boiling or vaporization. And of course we can go the other way, and this occurs if you have a cold glass of say, sweet tea on a hot, humid day. On the outside of your glass, you get some condensation. You've got some water vapor that condenses back to the liquid phase, so this is condensation. Now we can go from solids to liquids and back again. We can go from liquids to gases and back again. Can we go from solids to gas directly without going through a liquid first? I mean, clearly we can melt ice and turn it into water and then boil that water, but can we go straight from ice to water vapor? And it turns out we can. Now, this process is called subliming or sublimation. And of course we can go the other way too. We can have a gas that turns directly into a solid without going to a liquid state first. And that's called deposition. Because you're depositing the solid from the gas phase. So, now we have 6 transitions that will get us between any of our 3 phases. Again, we're ignoring the plasma because a plasma is essentially the gas phase that's been ionized. You have an ionized gas. And so we're going to ignore that. So, melting and boiling involves breaking intermolecular forces. To go from the solid to the liquid, you have to break just a small number of intermolecular forces. To go from the liquid to the gas phase, you have to break all the rest of the intermolecular forces. So, in order to break those intermolecular forces, we have to put in some energy. Which usually we do by heating. So heating gives additional kinetic energy to our molecules. That gives them the energy required to break those intermolecular forces. So we take one of our molecules, say from the solid state, and we give it enough kinetic energy to slide past, to break maybe one or two of its intermolecular bonds, but keep all the rest intact, and then it enables it to slide past some of its neighbors, and then it will form some more intermolecular bonds on the other side. And if we continue to heat up, we are moving our molecules faster and faster, and at some point, some of those molecules, say this one, has enough energy to break all of the intermolecular bonds, holding it in the liquid phase, and now it leaves and it goes into the gas phase. And then it has essentially no intermolecular forces unless it's in the process of a collision. So going the other way, condensation and deposition involve forming our intermolecular forces, like forming our intermolecular bonds. So cooling our substance down decreases the kinetic energy of our molecules, decreasing their ability to escape the intermolecular forces, and that means that when a molecule comes in, if it doesn't have enough kinetic energy to escape from the surface, then it has to remain as a liquid in the liquid phase. Or eventually at the solid phase, once you cool down enough, then the molecule doesn't have enough energy to break any of the intermolecular forces, and now it can't move out of place at all. It can still wiggle a little bit within place, but it can't move past any of its neighbors. And so now you have a solid. So melting and boiling points indicate the relative strength of our intermolecular forces. So a substance with a higher boiling point has stronger attractive intermolecular forces holding the molecules together, and thus it requires more energy to overcome the intermolecular forces. Because in order to boil, you have to break all of the intermolecular forces. So let's look at something like oxygen. Oxygen boils at 90 Kelvin, which means it has a relatively low intermolecular forces holding the oxygen molecules together. When we go to something like ammonia, NH3, we have a much higher boiling point. It's still a gas at room temperature, you notice. And so, because room temperature is above 240 Kelvin, but it's much closer. You can liquefy the ammonia much easier than you can the oxygen. Phosphine, the pH 3, has a lower boiling point than the ammonia does. And the water, of course, boils at 373. So now let's look at which of our three types of intermolecular forces, I'm ignoring here the ion dipole forces, which of our types, which of our intermolecular force types do each of our molecules exhibit? So let's look at oxygen. Does oxygen have dispersion forces? Pause the video and think about it. Yeah, it does. Of course, everything has dispersion forces. So I'm going to say yes, each of these molecules has dispersion forces. So now let's look at dipole-dipole forces. I want you to think about the structure of each of these molecules. If you can't see it in your head, pause the video, write out the Lewis dot structure. So oxygen doesn't have any dipole-dipole forces because you've got a homonuclear diatomic molecule. So the electronegativity difference between the two atoms is, of course, 0 because they're the same atom, the same type of atom, the same element. And so it can't have a dipole, so it can't have dipole-dipole forces, and it can't have any hydrogen bonding. The ammonia molecule does have a dipole. It's a polar molecule. The phosphine is a polar molecule because it's essentially the same structure as the ammonia, only we've replaced the nitrogen atom with a phosphorus. Note that in both of these cases, the electronic geometry about the nitrogen or phosphorus is tetrahedral, but they each have a lone pair on the central atom, the nitrogen or phosphorus, and that makes the molecular geometry trigonal pyramidal, and so it's polar, and so both of them have dipole-dipole forces. The water, of course, we know is polar, and so that has dipole-dipole forces in it. So now let's look at hydrogen bonding. Well, oxygen doesn't have any hydrogen atoms in it, so it can't have any hydrogen bonding. The ammonia has has hydrogens. It has a hydrogen bonded to a nitrogen. Remember, for hydrogen bonding, we need a hydrogen atom bound to a very electronegative atom, so a nitrogen, oxygen, or fluorine. We have that in this case. that nitrogen has a lone pair of electrons, so the ammonia has hydrogen bonding. The phosphine, it has the same structure as the ammonia, except that phosphorus isn't quite electronegative enough for us to have hydrogen bonding. So we don't have hydrogen bonding for the phosphine, which is why the boiling point of the phosphine is lower than the boiling point of the ammonia is, even though the dispersion forces for phosphine should be higher than the dispersion forces for ammonia because the phosphine has a larger molar mass. It's true, the dispersion forces of phosphine are higher, but the ammonia has the hydrogen bonding, which is stronger. It also has the dipole-dipole bonding, which is going to be stronger because the ammonia is a smaller molecule. And remember, dipole-dipole forces scale inversely with the size of our molecules. As our molecules get bigger, those dipole-dipole forces get weaker because the dipoles get farther apart. So now let's look at water. Water, of course, we know has hydrogen bonding because we have an oxygen atom that's bound to a hydrogen, or a hydrogen bound to an oxygen. So the oxygen is very electronegative. That oxygen atom has a lone pair of electrons. It has two lone pairs of electrons, actually. And so we have hydrogen bonding there. And now, notice that the hydrogen bonding in this case causes the water molecule to have a significantly higher boiling point than the ammonia does, because the oxygen is significantly more electronegative than the nitrogen is. And that means that the water has it has much stronger intermolecular forces than the ammonia does, and that means its boiling point is even higher than the ammonia's. So notice that the oxygen, which only has the dispersion forces, has a very low boiling point. The phosphine, which has dipole-dipole but not hydrogen bonding, has the next lowest boiling point. And then the ammonia, which has weaker hydrogen bonding than the water does, has the next lowest. And then the water, of course, has the highest boiling point of those four. So, as a solid, the molecules are moving very slowly and do not have enough kinetic energy to move past one another. And to become a liquid, enough energy has to be added in the form of heat, usually, in order for the molecules to move past one another. They have to break some of those intermolecular bonds. So how much energy has to be added is determined by the strength of the intermolecular forces. So this energy is called the heat of fusion, or enthalpy of fusion. So delta H, fusion. So the heat of fusion of ice, for reference, is 6.01 kilojoules per mole. We'll come back to that in a minute. So if we add heat, we add some amount of heat over time, let's say, and we measure the temperature. So we start out with, say, solid water, and it's at some temperature. As we add some heat, the temperature rises and rises until we get to some point, and then the temperature no longer increases. But at that temperature, at that point now, as we add heat, the temperature no longer changes, but we start to melt our solid. And so on the left side here, over here in section A, we have only solid phase, so we have only ice. And then here we have 100% ice, and on the right edge here, there we have 100% liquid, and in between we're transitioning from pure solid to pure liquid. So we're melting as we move to the right. If we move back to the left, we're freezing again. And once we've reached this point, now we've melted all of our solid, and now as we add heat, that heat is going to increase the temperature. Note that the temperature didn't increase in this section because the heat that we're adding is not going to increase the kinetic energy of our molecules. It's going to break the intermolecular forces. And so the molecules are moving just as fast there as they are over here, even though we've added a whole bunch more heat. Because all of that heat has not gone to increase the speed of motion of our molecules, it's just gone to breaking those intermolecular forces. Our molecules are a little bit farther apart, maybe. They're no longer bound together quite as tightly, but they're not moving any faster. And then once we've melted all of our molecules, once we've melted all of our solid, then that heat, as we add the heat, the temperature rises again until we get to the boiling point. So note that this temperature over here was the freezing point, or the melting point. This temperature here is the boiling point, or the condensation point. So once we've reached this point, we're at 100% liquid, but now our liquid is ready to boil. We've added so much kinetic energy that if we add any more, now the liquid is going to begin to boil. the molecules inside will have enough kinetic energy to escape the intermolecular forces of their neighbors and leave into the gas phase. And so as we transition from this point to this point, we're boiling, we're vaporizing as we move to the right, we're condensing as we move to the left. So we go from 100% liquid to 100% gas. And then at that point, as we add heat, the temperature of our gas goes up, and that goes up forever and ever. If we keep adding heat, the temperature will just keep going up. We can again go back to the left, pulling out heat, removing heat, or releasing heat from our system causes the temperature to drop, and then the temperature will stabilize as we condense until we get all of our vapor, all of our gas to condense out as liquid, and then the temperature will drop again until we begin to freeze, and then the temperature will be stabilized until we get all of our until we freeze all of our substance, and then the temperature will drop again. And of course then there's some point at which we've reached absolute zero, and now we can't remove any more heat. All of our kinetic energy of our molecules is gone. Now of course we can't actually get there, but that's a topic for another time. So let's talk now about vapor pressure. So this is the partial pressure of a substance above the liquid of that substance. So remember that a vapor is slightly different than a gas. It's essentially the gas phase, only the temperature that we're at is below the boiling point of our liquid, or below the sublimation point of our solid. So the vapor pressure is how much pressure there is from that substance above the liquid of that substance, or solid of that substance. So the vapor pressure increases with increasing temperature, because as we get closer and closer to the boiling point, the vapor pressure gets higher and higher. So in order to escape the liquid, remember the molecules must have enough kinetic energy to overcome the intermolecular forces. So as we heat up our substance, more and more of those molecules, a larger and larger fraction of those molecules, have enough kinetic energy to escape to break the intermolecular forces holding it to its neighbors, and thus leave and go into the vapor phase. So this energy, the amount of energy that is needed to break those intermolecular forces, is called the heat of vaporization, or the enthalpy of vaporization, delta H vape. And for water, the enthalpy of vaporization is 40.7 kilojoules per mole. Now remember, the enthalpy of fusion for water was only around 6 kilojoules per mole. So it takes a lot more energy to boil water than it does to melt it. Now, also note that this energy here is the reason why steam, if you stick your hand in steam, it's going to hurt a lot more than sticking your hand in boiling water. Because the boiling water, yeah, it's very hot, but the steam has the same temperature, but it has this additional 40.7 kilojoules per mole of energy. So if you stick your hand in steam, not only does the temperature of the steam drop to add heat to your hand, but it can also condense out on your hand, and every mole of water that condenses on your hand gives your hand 40.7 kilojoules per mole of energy that the liquid water didn't have. And of course now it's liquid water stuck on your skin, and it's going to continue to cool down as it heats up your skin, and so it's going to hurt a lot. So steam hurts much more than water does at the same temperature. Alright, so remember that the speed, the kinetic energy of molecules is a distribution. Right? We have a distribution that looks something like this. And at low temperature, we have a distribution like this. And at higher temperature, that distribution shifts to the right. Now, this is drawn a little bit incorrectly. This really shouldn't go all the way down to zero. It should, there should be some fraction even over here, no matter what temperature we get to. So it really should just spread out more as we shift to higher temperature, not move the whole curve to the right. But what I want to point out is that at low temperature, there's some amount of energy right here. This is the minimum kinetic energy needed. In this case, it says to provide the activation energy, but let's assume the activation energy in this case refers to boiling. In order to break the intermolecular forces, we need, say, this amount of energy. Well, at low temperature, just a small fraction, just this much of our molecules, that small fraction of our molecules will be able to break those intermolecular forces. So at low temperature, the number of molecules in the gas phase will be relatively low. But if we increase the temperature, so we go from this curve to this curve, now we have all of these molecules. So we have a much, much higher chance that any one molecule we have has enough energy to leave the liquid phase and go into the gas. And that means that at the higher temperature, the vapor pressure should be higher. And at some point, we shift this curve far enough to the right that this peak is past this point, past that energy. Right? If we get most of our molecules way over here on the right side, that means that most of our molecules have loads of energy, plenty of energy to vaporize, and that's when we begin to boil, right? Or that's when we've already boiled our substance. So, only a fraction of our molecules in the liquid have a high enough speed, and thus kinetic energy, to escape the liquid, and the fraction of our molecules with enough kinetic energy increases as we increase the temperature. It will also increase if we lower the energy that's required, so if we lower the strength of intermolecular forces. So substances with high vapor pressures at some certain temperature we call volatile. They're more volatile if they boil at a lower temperature or if their vapor pressures are higher. And when the vapor pressure becomes equal to the pressure above the liquid, then the liquid boils. So when if you have, say, 1 atmosphere of pressure, as you have if you have a container that's open to air, when the vapor pressure of that liquid reaches 760 torr, 1 atmosphere, that's when the liquid boils. Because at that point, now molecules that are deep inside the liquid, not right at the surface, but deep inside, they can now form bubbles of gas. And those bubbles then come up to the surface and leave. So if you have water at 1 atmosphere, water, of course, boils at 100 degrees C. Well, the vapor pressure of water at 100 degrees C is 760 torr, 1 atmosphere. At temperatures lower than that, then the vapor pressure is lower. At temperatures higher than that, the vapor pressure of water is higher than that. So if you have something like a pressure cooker, you increase the pressure by trapping some of that water vapor inside the pressure cooker. You increase the pressure. If you increase to, say, 2 atmospheres, the pressure or the temperature, the boiling point of water now goes up to, it's around 110 degrees Celsius. So now you can cook your food instead of at 100 degrees C as if it would if the water were boiling in at 1 atmosphere. You can increase the temperature some, and that means that those chemical reactions occur faster. The cooking occurs faster. You actually get more tender meat, but it cooks much faster at higher temperatures, like in a pressure cooker, than it would boiling at 1 atmosphere. So when the vapor pressure becomes equal to the vapor pressure above the liquid boils. So if we look at the vapor pressure of water at 0 degrees C, it's basically ready to turn into ice. The vapor pressure of water is only 4.6 torr, and it increases to 17.5 if we move up to 20 degrees C. We move up to 40 degrees C, then the vapor pressure is 55.3 torr, and so on until we get to 100 degrees C, where it's 760 torr. And of course, it goes up from there. So now let's talk about sublimation, going directly from the solid to the gas phase. The energy required to change from a solid to a gas at the same temperature is the enthalpy of sublimation, delta H sub. Now, remember that in order to go from the solid phase to the gas phase, you have to break all of the intermolecular forces. And to go from the solid phase to the liquid phase, you have to break just some of the intermolecular forces. And to go from the liquid phase to the gas phase, you have to break all the rest of the intermolecular forces. Which means that going from the solid to liquid to gas, you're breaking all of the intermolecular forces, you're just doing it in 2 steps. First you're breaking some, then you're breaking the rest. Well, the amount of energy it takes to break some and then the rest is the same as the amount of energy it takes to break all of them. So with sublimation, you're breaking all of them in 1 step. Just like in Hess's law, you're going from solid to gas. If you do it in 1 step, that's the same energy change, the same enthalpy change as doing it in 2 steps. So the enthalpy of sublimation is equal to the enthalpy of fusion plus the enthalpy of vaporization. So now let's talk a little bit about equilibrium. So at equilibrium, the state of a system, this is the state a system is in when it's not changing. Now, by not changing, we don't necessarily mean that nothing is happening, because we have 2 different types of equilibrium. We have static equilibrium and dynamic equilibrium. With a static equilibrium, nothing in the system is changing at all. Nothing is happening. But with a dynamic equilibrium, 2 or more opposing processes are occurring simultaneously at equal rates. So this is usually what we mean by equilibrium. In chemistry, this is what we mean. So a static equilibrium is like if I take a ball and I put it on a table and it's not moving anywhere. That's a static equilibrium. Nothing is happening. The ball isn't moving one direction and then back or something. Right? It's not moving at all. Nothing is happening. But with a dynamic equilibrium, this is something like if we have water at some temperature, say 25 degrees C, and we've got it in a closed container, there's some molecules that are in the liquid phase and some molecules in the gas phase, in the vapor phase. Well, some of the molecules in the vapor phase may collide with the liquid surface and lose a little bit of energy and give a little bit of that energy to another molecule that's in the liquid phase. Well, that original molecule, the one that was in the gas phase, in the vapor phase, may condense and stay in the liquid phase if it no longer has enough kinetic energy to leave the liquid phase. But another molecule that gains some of that kinetic energy may now have enough kinetic energy to leave the liquid phase by breaking its intermolecular forces. And so, over time, for every molecule that enters the liquid phase, we have one molecule that leaves the liquid phase and enters the gas phase. And so, in this way, stuff is happening. The molecules are moving back and forth. Some of the gas molecules, some of the vapor phase molecules are moving into the liquid. Some of the liquid molecules are moving into the vapor phase. But over time, the number of molecules in the liquid phase and the number of molecules in the gas phase are constant. Because we have these two forces that are each occurring, two processes that are each occurring. The condensation and the vaporization are each occurring at the same rate. And if they're occurring at the same rate, then effectively there's no net change, even though molecules are doing things. They're moving where the ball on the table isn't moving. Right? So in chemistry we have dynamic equilibria. If you're looking at the macro scale, nothing is occurring. But if you look at the micro scale, at the molecules themselves, there's a lot happening. It's just that one process is being totally balanced by the other process, by the reverse. So a gas-liquid system at equilibrium is a dynamic equilibrium. So vaporization is occurring, our molecules are leaving the liquid phase by breaking the intermolecular forces, and condensation is occurring, our molecules are leaving the gas phase by losing kinetic energy to other molecules, and are then trapped in the liquid phase by the intermolecular forces. And vaporization of the liquid is occurring at the same rate as condensation of the gas. And so here we have a picture of that. So we have vaporization going on. So initially, if we trap our liquid in, say, a bell jar, we have very little of our vapor phase up here. And initially, some of our molecules move up. And over time, we get more and more molecules up there. And some of them begin then to go back into our liquid phase. And eventually, the rate at which the molecules are leaving the liquid phase is the same at which the molecules are entering the liquid phase. And so we've attained equilibrium in this case. So that was vapor pressure and changes of state.